Buenas tardes, jóvenes, qué bueno que nos acompañan el día de hoy a esta charla pública que está titulada como el piano cósmico. Es presentada por el doctor Guillermo Tejeda Muñoz, que es profesor investigador de la Facultad de Ciencias Físico-Matemáticas de la UAP, especializado en detectores de partículas, de los cuales se pone, son instalados los colisionadores, ¿no? Entonces, en esta ocasión, él nos va a hablar sobre una invención que realizó él en conjunto con su colega, el doctor Arturo Fernández, basado justo en esta idea de los detectores de partículas. Entonces, démosle una bienvenida, por favor. Adelante, Guillermo. Gracias por venir.
Hola, bueno, buenas tardes. Gracias por estar acá. Bueno, la plática de esta tarde es sobre un detector de partículas que se llama piano cósmico, que están viendo funcionar ahorita. Lo voy a dejar trabajando durante la plática, que es breve, para que vayan entendiendo poco a poco qué es lo que estamos viendo con estas lucecitas y ahorita subo el volumen. El piano cósmico, como les comenté, es un detector de partículas para propósitos de divulgación, para mostrar a todos los que no tengan mucha relación con el mundo de los detectores, física de partículas, física, qué es un detector y cómo funciona, y cómo podemos percibir el paso de la partícula. Entonces, ya lo viendo porque música, ¿no? Antes teníamos unos detectores de 8, ya no llegan los días ciertos. Voy a mostrar rápido cómo se ve incluido dónde se ha mostrado, desde cuándo se inventó y un poco sobre lo nuevo que se está construyendo alrededor de este detector. Pues bueno, vamos a hacerlo muy rápido. Primero, estamos viendo que hay unas flashes de luz, ¿verdad? Y un sonidito que ahorita lo vamos a... Cada vez que una lucecita prende, escuchamos un sonidito. Ese sonidito está producido por algo que está llegando justo en este momento donde estamos. No importa dónde pongamos un detector, va a prender. ¿Por qué? Pues porque hay unas cosas que se llaman rayos cósmicos. Son partículas, núcleos de átomos, Tierra generalmente, que viajan por el universo, llegan a la atmósfera de la Tierra, chocan con alguna molécula de ozono generalmente, partículas secundarias, esas partículas secundarias colisionan con otras partículas y pues así se obtiene lo que es la cascada de partículas, ¿no? Acá a nivel de la superficie de la Tierra podemos verlo como si fuera una lluvia, ¿vale? Si pudiéramos ver esas partículas, una lluvia que están pasando por todos lados. Hay muchas partículas primarias que se producen a como unos 30 kilómetros de altura, pero a nivel del suelo solo estamos viendo usualmente lo que son muones, una partícula muy similar a lo que es un electrón, pero mucho más pesado, ¿no? Por eso tiene la suficiente, bueno, tiene el tiempo para llegar a la superficie de la Tierra y todavía atravesar varios cientos de roca. Entonces, así son los rayos cósmicos, las partículas, y acá a nivel de la superficie, pues nos estarían atravesando estos muones. El rate de llegada de estas partículas es de aproximadamente 1 por centímetro cuadrado por minuto, y para partículas mucho más energéticas es de 1 por kilómetro cuadrado por siglo, cuando tienen energías demasiado altas. Entonces, pues eso es lo que estamos viendo, partículas que llegan del universo, en algún lugar del universo se aceleraron, viajaron por todo el espacio hasta encontrarse con la Tierra y producir este lluvia de partículas. Entonces, el piano cósmico pues es un detector de partículas, como les comentaba, hecho a base de plástico, un plástico centellador, es algo parecido al acrílico, vidrio, no se rompe tan fácil como el vidrio, el acrílico, el cual tiene la propiedad de que cuando pasa una partícula o fotón, pues emite luz. ¿Vale? Entonces esa luz la colectamos por fibra óptica y con electrónica pues procesamos toda la información y así encontramos estas partículas. Entonces así es, este es un material muy eh, importante, muy básico en el área de partículas, ¿no? Hay muchos detectores en el mundo que están construidos con este material. Actualmente pues, hay muchos funcionando y todavía hay muchos detectores que se están planeando. Entonces, tomando como base este fenómeno que sucede en el universo y en la Tierra, pues inventó lo que es el piano cósmico. Es una manera de mostrar cuándo dónde está pasando una partícula, un rayo cósmico, un muón. Entonces tenemos el detector, el módulo, que están viendo ahí, y bueno, pues tenemos los foquitos y la electrónica que nos están mostrando eh, estos fenómenos. Eh, entonces, cuando ven flashear uno de esos módulos, significa que en ese momento acaba de pasar una partícula, un muón. Entonces, como se pueden ver, pues pasan muchos. Eh, Podemos ajustar el rey de detección para detectar más partículas, pero bueno, es para que sea relativamente agradable, ¿no? Escucharlo. El piano cósmico, pues bueno, tiene una larga historia. Empezó básicamente en el 2004, cuando se presentó en el Open Day del CERN, es decir, se preparó un experimento para mostrar a la gente que iba a visitar el CERN, festejando su 50 aniversario. Quería que se instalar algo que vieran, para que la gente viera cómo funcionaba un detector. Entonces hizo una versión muy simple de lo que es el piano cósmico, con focos convencionales, y de ahí empezó a evolucionar y ha ido por muchos lados, ¿no? Por muchos lados del mundo, Barcelona, Polonia, en varios eventos del CERN, más puertas abiertas del CERN, en Torino, eh, acá en Puebla, hay una sala de adquisición de Alice, está el CERN, en Manchester, en Bristol, en Bulgaria, en 2018. Fue un concierto bastante bonito, les voy a mostrar unos videos. Acá está un piano, un violín, una flauta, un teremín y el piano cósmico. Un concierto de instrumentos musicales, ¿no? Y acá también en el CCU una vez presentó un evento bastante grande. Esto fue en el 2019. Eh, entonces, vean, este es un ejemplo de cómo puede sonar el piano cósmico con un piano normal. Un concierto. Esa eh, composición la hizo esta chica, que es una, en ese, era muy famosa, una estudiante de música, muy famosa en Bulgaria, que precisamente escribió esa composición para el piano. Bueno, era como el premio que recibió la mejor estudiante de esa generación, ¿no? Hacer esa composición. Acá hay otro video. Acá este chico se llama Horacio Fernández. Él es músico, compositor. Actualmente está estudiando su maestría en Juilliard, en Nueva York. Y también, ¿no? Él es uno de los que está trabajando muy fuerte con el piano para hacer, pues, composiciones. Otro evento. También es la misma chica, pero la otra parte de su composición. Este salón es el salón de conciertos de la Escuela de Música de Bulgaria. Entonces es un salón muy bonito, tiene su escenario bastante profesional. Y acá está también escribió esta composición para estos instrumentos. Se apellida Sare, Roger Sare. Pues bueno, están todos tocando y ellos ya tenían todo esto, cómo iban a activar los detectores. Y bueno, el teremín, no sé si han escuchado, es un instrumento también que utiliza física para funcionar, que es pues, básicamente interferencia electromagnética. Entonces, es un instrumento también bastante interesante y novedoso. Ahora, hay un nuevo proyecto que se desarrolló, que es el árbol cósmico. Acá se puede ver los procesos que llevamos para la construcción, para crear el árbol, los detectores, 5 módulos, la electrónica, todo se hace acá en la universidad, hasta que tenemos ya el árbol cósmico con los módulos aquí para detectar los muones. Y ya pues se ha mejorado mucho el sonido, como pueden ver. Tiene un sonido mucho más relajante, porque algunos músicos, como pueden ver, nos han ayudado a elegir estas frecuencias que faciliten pues llamar la atención, ¿no?, del público y sea más agradable. Entonces esta música ya es mucho más agradable, ¿no? Como pueden ver, los módulos prenden igual que este, y aparte las ramas del árbol también se iluminan conforme prenden los árboles. En la noche se ve muy bonito. El video. Este detector de partículas en forma de árbol está instalado en el Museo del Meteorito en Charca, San Luis Potosí. Se instaló en el 2021. Y allá, si tienen por ahí, van a poder ver. Entonces, pues, es un proyecto que, como ven, lleva bastantes años de trabajo. Desde el 2004 ha ido evolucionando y se ha seguido mejorando porque pues el interés que genera la mayoría de las personas es muy grande. Pues, en todos muchos lados del mundo que se ha presentado, pues siempre quieren uno, quieren usarlo. Y la idea es que ustedes vengan y aparte de que se vea la detección de partículas, se hagan algunos otros experimentos como detección de partículas, variar el range de partículas dependiendo del ángulo de llegada de los pulmones. Y pues con la electrónica podemos contar esos eventos. Entonces, pues bueno, la foto final del evento que se hizo en Sofía, Bulgaria esa vez, muy bonito. Y bueno, vamos a subir ahora el volumen para que la gente nos vea. No suena tan bonito como el otro que hicimos, es una versión anterior, porque es la portátil. Entonces, bueno, pues pues ya sabemos qué es esto, ¿no? Es un detector de partículas, y a donde lo pongamos vamos a ver que siempre va a estar prendiendo, activándose. Entonces, si lo ponemos sobre su cabeza, va a estar prendiendo y indica que quizás esa partícula se atravesó, ¿no? No se preocupen, no es peligroso, es radiación cósmica natural, así que nuestro cuerpo está acostumbrado a eso. Pero bueno, ahora ya sabemos todo eso. ¿Tienen alguna pregunta? Terminamos. De todos modos, vienen de la prepa, mañana se va a volver a presentar ya con un poco más de explicación. ¿Preguntas? ¿Comentarios?
Muy bien, primero le agradecemos al doctor Guillermo su presentación. Y ahora sí, tenemos tiempo para algunas preguntas.
yo tengo una pregunta. No sé si me perdí la primera parte y lo mencionó. La frecuencia de estas notas están asociadas con la correspondiente al ion que se detecta, o nada más es a una frecuencia que asignamos local y que pueden también.
Sí, pues el sonidito que cada módulo ya está listo para cada detector. Es cada módulo es diferente, pero el mismo módulo siempre va a tener. Sí, depende. Hay una versión que hicimos una vez de ese detector al cual, dependiendo de la energía de la partícula, el tono cambia, pero es un poquito más aleatorio. Entonces, una de estos compositores que nos han ayudado a desarrollar la parte de la música, nos comentó algo de quizás algunos de ustedes que les guste la música sepan más, le llaman la teoría pentatónica, que nos dice que básicamente nuestro oído evolucionó a que una combinación de 5 sonidos, como sea la combinación de estos 5 sonidos, va a ser agradable para nuestro oído, sin importar la frecuencia, el orden, ¿no? Entonces, bueno, acá tenemos 4 detectores, pero en los anteriores siempre llevamos 5 detectores, precisamente para jugar con eso, ¿no? Con lo que es la teoría pentatónica. Y por eso también los sonidos ya están fijos, para no variar, no salirnos de ese rango. Si en la versión de 8 detectores es demasiado y se vuelve ruidoso, demasiado ruidoso. Entonces, digamos que los 5 módulos que generalmente se presentan tienen ese fundamento en la música. Y la frecuencia están seleccionadas también para que sea más despierte el interés de las personas, ¿no? O en promedio, ¿no? Sabemos que no todos los seres humanos respondemos de la misma manera, ¿no? Entonces, la idea es que sea algo que a la mayoría le pueda interesar y es para pues llamar la atención.
Gracias por la pregunta. ¿Alguna otra pregunta? ¿Comentario?
No tengan miedo.
¿Puede repetirme, por favor, cuál es la forma o el funcionamiento del sensor? O sea, ¿a base de qué es que detecta la partícula?
Sí, el detector tiene como centro algo que es como esto, es un plástico centellador, me parece un plástico. El plástico, este plástico está dopado con unos materiales que hacen que cuando pasa una partícula, cuando está forrado, completamente aislado de la luz, pasa una partícula cargada, excita a los átomos y esa excitación produce el fenómeno de centelleo, que se llama plástico centellador, es decir, los electrones cambian de órbita, se excita, se excita y emite fotones. Esos fotones están en la longitud de onda del azul, moradito. Si sacamos este plástico al sol, se va a ver de los lados como moradito. Es por eso, porque empieza a centellar. Y si pueden ver acá unos puntitos verdes, como si fueran unos ojitos, quizás, ahorita si quieren pasar, se los muestro, se ven unos puntitos, a ver, pásenlos. Esa es una fibra de corrimiento de fase. Lo que hace es que absorbe toda la luz que emite el plástico y la remite en el verde, porque ahí es donde está su máxima eficiencia de detección de nuestros detectores, de nuestros sensores que van acá. Son 2 detectores que colectan esa luz y pues con esta electrónica hacemos la coincidencia de cuando ven los 2 ese centelleo y en ese momento se considera que es un evento válido y emite, pues nosotros emitimos ya un pulso que es que hace que veamos este fenómeno. Entonces, pues así es como, de forma muy general, es como funciona. La fibra, pues es una fibra plástica, como menciona, que la van a ver verde, pero es porque está emitiendo ahorita, pues está absorbiendo todo lo que el plástico está emitiendo, centellando, y por eso se ve verde, ¿no? Y ese foquito, en el centro de las fibras van a ver como si tuvieran un foquito. Esa es la luz que se emite y que colectamos con esos detectores, pero obviamente la luz de las partículas que llegan y pasan por acá es muy pequeñita, así que pues se tiene que amplificar y con más electrónica se hacen todas las coincidencias y combinaciones para que ya podamos escucharlo así.
Y ya nada más por curiosidad, ¿la placa base es Arduino o qué es?
Esta electrónica o esta primera versión son microcontroladores. Todo el código está hecho en ensamblador. Si algunos de ustedes conocen ensamblador, entonces ya sabrán que es un caos todo lo que hay allá adentro. Pero la versión nueva funciona, bueno, es la electrónica que nosotros desarrollamos. Esto es un FPGA y esto es una Raspberry. Entonces, si saben programar en Python, todo está en Python. Ahí, un poquito más fácil. Porque tiene una interfase ya gráfica y es touch, entonces bueno, está mucho más desarrollado eso. ¿Otra pregunta?
¿Cuál es el mecanismo que hace que no haya como interferencia de otras partículas cargadas?
Esa pregunta es bastante interesante y complicada. Básicamente cualquier partícula cargada puede activar el proceso de detección en los módulos. Cualquier partícula cargada, como dijo su compañero. Acá en el medio ambiente, generalmente lo que nos rodea, siempre tenemos muchos electrones que se están moviendo, ¿no? Si tienen la suficiente energía de atravesar el forro que cubre a los plásticos y impacta con alguna de las moléculas del plástico centellador, que atraviesa todo este forro, pues va a activarlo. Pero eso es muy poco probable. Las partículas que acá donde estamos pueden realizar ese proceso son los muones, por la masa que tienen y la energía que tienen. ¿Vale? Entonces, por eso se forra, porque si no lo forramos, la luz entra y va a activar al detector y vamos a ver mucho. Esto nunca dejaría de sonar, ¿no? Entonces, por eso lo forramos, para aislarlo de la luz. Y pues este forro tiene varias capas, precisamente para aislarlo mejor y evitar que otras partículas no tan pesadas, con no tanta energía, activen eso. Digamos que eso es nuestro filtro. Y de esta forma, pues garantizamos que son muones. Aún así, eso no nos excluye de que estemos viendo quizás otras partículas ocasionalmente. Puede ser que algunas otras partículas cargadas pues estén ahí detectándose, pero principalmente la mayoría son muones. En los experimentos, ya donde se hacen física experimental, también pasa eso y se utilizan otros medios, ¿no? Otros procesos para eliminar las partículas que no nos interesan. Pero bueno, en este caso, pues así es como lo hacemos.
Muchas gracias.
Vamos a la última pregunta, porque hay otra actividad después de esto.
El detector se puede utilizar para otros instrumentos que no fuera el piano, por ejemplo, guitarra, violín, flauta.
Sí, precisamente hace un par de meses, 2 meses, hablamos con no me acuerdo del nombre, es un músico de Sudáfrica y él tienen un museo, es el jefe del museo. Y él ellos tienen una especie de instrumentos como guitarras. Y la idea es que se aplique así. Pero no solo se piensa utilizar de esa manera, ¿no? Como piano cósmico. Algunos psicólogos que les ha gustado también este concepto, dicen que podría aplicarse como un equipo de terapia para ver cómo reaccionan las personas ajustando los colores, su estado de ánimo, ciertas características, y ponerlo en una cabina, en la cual solo vea esas frecuencias y los sonidos, todo sería oscuro y nada más vería eso. Entonces es una de las ideas de desarrollo que también están trabajando, es eso, ¿no? Ver si se puede aplicar como una especie de equipo de terapia, obviamente con las frecuencias adecuadas y colores adecuados para cada caso, ¿no? hiperactividad o algún detalle ahí que se quiera, de la personalidad que quiera analizarse, ¿no? De ciertas personas. Entonces sí, pues la verdad es que de diferentes áreas se ha visto cómo se puede aplicar, ¿no? La idea original pues es la música y despertar nuestra curiosidad, activar nuestros sentidos para saber qué es lo que pasa y aprender un poco de física, ¿no? De forma muy interactiva.
Gracias.
Gracias. Bueno, yo creo que acá terminamos. Muchas gracias a todos.
Bueno, muchas gracias por haber venido. Ahorita por cuestiones de logística tuvimos como ver la charla del profesor Rollón, la físico-matemática, pero por supuesto también muchas gracias por haber venido. No, y estén atentos porque a lo largo del próximo año, junto con los profesores, vamos a estar realizando varios ahora que están retomando las actividades presenciales. Por ejemplo, está el concurso de Beamline School, que es donde estudiantes de prepa aplican, propone un experimento para que se realice un examen. Y los ganadores serán todos ganadores. Ese tipo de detalles, clases maestras. Entonces, estén atentos porque este tipo de actividades las vamos a retomar en el próximo. Muy amables y muchas gracias por haber venido.
So maybe we will be able to produce some new particles that disappear nowadays. So this is a bit the idea why we built the LHC. So we could say from this point of view that the LHC, in fact, as I said, is probably the hottest point in the universe today. Because the temperature that we have at the LHC is 10 to the power 17. It's not 17 degrees as written here, but 10 to the power 17 degrees. It means that it's much hotter than the temperature of the sun. Of course, this is on a very, very small part, where, for instance, the proton collide. It's not on a wide scale like the sun. I mean, obviously, it's really on a very small part, but we reach this kind of temperature. And just to give you an idea, the temperature of the sun is 10 to the 7 degrees. So it's 10 orders of magnitude higher, the temperature that we reach locally at the interaction point at the LHC. Just to give you a feeling of the kind of conditions that we are reproducing at the LHC. Then, also, on the other hand, I mean, at the same time, the LHC, you can say that it's probably the coldest point on Earth. Because the machine is completely cooled down, I mean, to keep the beams in interaction and inside the LHC, we have to use huge fridge and keep the machine at a temperature which is minus 271 degrees. And on the full scale of the LHC, which is about, let's say, 40 kilometers. So we have to keep this kind of temperature on the full scale of the LHC. And it needs about 10,000 tons of nitrogen, liquid nitrogen, and in addition 100 tons of liquid helium to maintain the LHC at this kind of temperature. So it's a bit funny that it is the hottest element of the universe, and at the same time probably the coldest element, at least on Earth, maybe not of the universe. So, in addition, how can we consider a detector? A detector, you want to, for instance, when you have two protons that interact, you want to measure all the particles that are produced in the final state after the interaction. So what we do is like a camera. You all have a camera, so we want to take a photo of what is going on when these two protons interact. So this is what is shown here, and you see this camera taking a photo of the interaction. But the difference is that we have about 100 million channels, because we take many channels, and we take also a photo every, basically, 25 nanoseconds. So we are able to take photos very, very often, using about the 40 million of photos per second. So this is basically like a camera, except that we don't measure only photons that your camera is doing, but we measure all kinds of radiation using our detector. But you have to see the detector as a camera that just want to take a picture of this interaction. Oops. So now let me discuss a bit the two main detectors that we have at the LHC that are called CMS and Atlas. Again, it's just to give you an idea of the size of the detectors, and at the end we will show you a small movie, so we will show you a bit how the detectors look like, and it's for those who have never been to CERN, to give you an idea how CERN look like. So but just let me show you this photo on the left, which is a Mount Rushmore in the US. I mean, maybe some of you have been there already, have seen it in reality. And you see in a way that is very big. You see the size of the trees. So you see it's a huge structure on the mountain. And we just put on top of it, on the left, this is the Atlas detector, and on the right, the CMS detector, just to give you an idea of the size of this detector that we are talking about. So definitely it would not hold in this room. I mean, no way. So you need about a room of more than 10 floors to be able to locate this detector. And also it's very heavy, because if you compare the weight of the CMS detector with the Eiffel Tower, CMS is even 30% heavier than the Eiffel Tower in Paris. Again, just to give you some idea. So now let us discuss a bit how we measure the particles that are produced during an interaction. And the idea is always the same. If you are in nuclear physics or high energy physics, what you want to do is to absorb the different particles that are produced after the collision. And in fact, the quantity of matter that is needed to absorb the particle depends on the particle. And this is always illustrated on this kind of diagram, which is here. You see the bottom, in the middle, there is the point of interaction, and there are different particles that are emitted. So first of all, you have what we call the tracking detector. So we measure the trajectory of the charged particles. Then, in a kind of orange, this is what we call the electromagnetic calorimeter. So electromagnetic calorimeter is dedicated for electron and photon. And then we move to the blue region, which is the hadronic calorimeter, and this is dedicated, for instance, for protons, for neutrons, because they need more material to be absorbed than the electron on the photon. So the idea is very simple. You have different layers that correspond to the amount of material which is needed to absorb the different particles. And at the end, this kind of grayish material that you see, this is what we call the muon spectrometer, because they need much more material to be absorbed. So this is basically, you need lots of steel, in fact, to absorb the muons. And there is one particle, if you see the dashed line, which is on the right, which is not absorbed at all. And in fact, this is the neutrino, because the neutrino, probably, as you know, they can even cross the Earth, most of them without interacting, so no hope that we can build a detector that will absorb my neutrino. So the way it will appear is by some missing energy, if you do some energy balance in the events, which will be the consequence of the presence of the neutrino. So it will be, we don't measure them directly, but they appear as some missing energy. So I just want to mention also the computing situation in Atlas or in CMS. So we produce million and million of data every day. So this is about, for instance, per year 2 million DVDs or 15 million CDs. So we would have already taken enough data to cover the distance between the Earth and the Moon, for instance. I mean, if you wanted to find all these CDs. So, and this led also to the concept of grid that you might have heard about it. In fact, the concept of grid that CERN developed is to use any computer on the planet which is on the grid, which is free. Let's assume that now, I mean now, what time is it? It's almost 6 o'clock. So it's about 1 a.m. in France. So 1 a.m. in France, there are not that many people working. So the computers are sitting free. So CERN is sending the data on these free computers. They are reconstructing the events, and then the data are sent back to CERN. Whereas, for instance, I don't know, in 4 or 5 hours from now, here in Mexico, the computer will be free, so we'll do the same trick. CERN will send some data here, the data will be reconstructed, and then we will send it back to CERN. So this is the concept of grid, which is to make a link between the different computers of the planet, so that we can benefit from the fact that we have different hours, different time scale on the planet. Okay, good. So now let's come a bit to the physics. So if I was asking you what is a proton, I guess many people would have told me, I mean, 2 up quark and 1 down quark. Probably this is the vision that people have, I mean, UD. So this is what people see. And also they know that this is quite small, so the size is an order of 1 Fermi, which is 10 to minus 15 meters. But it's not the vision that I have of the proton. The vision that I have of the proton is more the bottom one, so you still see these 2 quark and this down quark. But you see there are many strings which correspond to the gluons, we'll see in a minute. And there are also these small circles, which are purple and green, that corresponds to pair of quark and antiquark. So this is more the vision of the proton that I have than this pure 2 up quark and down quark. And we will see, in fact, why the proton is much more complicated than people think at first sight. So what do we do? So we in fact want to measure the structure of the proton as a function of 2 variables. So the horizontal variable is called Q square by the physicists, and it corresponds to the resolving power of your microscope. It means that if you have a bigger microscope or a bigger accelerator, in other words, you can reach higher values of Q square in order to see more details inside the proton about the structure. And the vertical length, you see that this is basically what the variable that we call x, or 1 over x, which corresponds to 1 of the momentum of the object inside the proton. So this is this kind of blue, red, and yellowish color object. And when x is decreasing, so when you go up along this diagram, it means that the momentum which is carried away by each of these constituents, which are the quark or the gluons, is basically decreasing. So this is why it leads to the structure of the proton that was just mentioned. You have at small x, which we can reach at the LHC, you can see a structure of many, many gluons and many quarks. And at some point, you can forget about these 2 up quark and the down quark, because they are not dominating at all. So you get this image, the proton, which is full of gluon and full of Q and Q pair, and you forget about this structure of the proton. And this will have some consequences that we are going to discuss now. But before we go there, let me discuss how we measure some interaction at the Large Hadron Collider. So what we do, we have proton 1, which collides with proton 2. And as I said, so you have these two complicated objects which are made of quarks and gluons, so this is the same for the two protons. And the way we do some measure, we wait for these two protons to collide, and we measure the particles that are produced. It means that the analysis that we need to do, and I will show you an example of an analysis, we need to identify interesting events in all the events which are taken at the LHC. We cannot tell the protons, please produce for me a top quark. I mean, of course, it's impossible. So it's only, there are some probability to produce different kind of particle, and this is the work of the physicist to find the interesting events and interesting interaction for us. So if you want to study the top quark, you want to have to identify some way, some method, in order to be sure that you had some top quarks that were produced in the interaction. So this is the way of the work of the physicist is doing, is from the simple interaction and all the events, all the interactions that we are recording, which are purely probabilistic. We want to identify the events which are interesting for us. And for some people, it will be top, that I was mentioning. For other people, it will be looking for supersymmetry. For other people, it will be study the proton structure, so measure the amount of quark in the proton. So it depends on the physics topics that you are doing. So let's come back basically to the standard model. So you know, we discussed already, we have the 6 quark. We already mentioned up, down. So there are also C like charm, S like strange, B like bottom, and T like top, which is the heaviest quark by far. Then we have the electrons. So we have 6 of them, electron, muon, and tau, and the neutrinos, which are associated to each lepton. And then the forces, which are basically the mediator, the particles which are mediator of the different forces. So you have gamma, which all of you know because it's electromagnetism. I mean, everybody has probably studied electromagnetism. In addition, we have G, which is a gluon, which is for the arc force, what we call quantum chromodynamics. And then we have Z and W, which are 2 bosons for what we call the weak force, which is basically they were discovered in the 90s at CERN. And in the middle, you see the letter H. Probably all of you have heard about it. So this is the Higgs boson that gave a Nobel Prize a few years ago, because this is the particle that gives mass basically to all matter, and like this chair or yourself, I mean, we would not exist if the Higgs were not existing. So, let me discuss. So this is a bit more complicated slide, but I want to introduce how we are doing analysis. A general analysis, let's say, in high energy physics. As I said, so we are physicists and we want to measure some top production. So we want to measure, to see some events that produce a top quark plus an anti-top quark. So how are we going to do that? So what we want to do is to consider the decay products of the top quark. So you see on the right, there is this T bar that decays into W, which decays itself in the red, which is an electron, and a neutrino. Neutrino, as we said, is a missing energy. Plus this greenish, which is here greenish area, which corresponds to the emission of a big quark. So this is the way that I will identify my T bar. It is by one lepton, this red lepton, again missing energy because there is a neutrino which is produced, then a big quark, so I need to measure this big quark. And for the other top, which is on the left, you have again a big quark, which is there in green, and you have also 2 non-massive quarks like U and D, which are the QQ, which are there in blue. So this is the decay of my second top. So what I am going to look, I'm going to look for events that shows 2 big quarks, 2 green ones, 1 lepton is in red, 1 missing energy, which is the neutrino in yellow, and 2 light, what we call jet light quarks, which are the 2 quarks which are here. So this is the way we try to identify these events by the decay products of what we want to look at. So then you request all these kind of particles to be produced in a special region of the detector, and this will be the events that you want to analyze. So this is the way that we select these kind of events in high energy physics. So now let me come to another domain. That's the domain that we want to study at LHC, and it's a completely new domain that has not yet been completely studied, and it's also difficult to analyze theoretically. which is what we call saturation. What I told you, if you remember, is that X decreasing, the number of objects inside my proton is getting very large. So the number of gluons or the number of quarks, you see this proton on the diagram on the right, it has a very high density of objects inside. And this is like what I showed you, like all these people, and let's say they are in the metro of Paris at peak hours. So these people, they are just compacted together because the metro is completely full. So when something hits them, especially, hopefully it doesn't happen often, but when they are pushed by something, you will have a kind of collective phenomenon because all these people are very close together, so they will move basically together. And this is exactly what happens with my gluons inside the proton. When you hit this object, which is extremely dense in terms of gluon, they will act like a collective object. We call it glass, in fact, like a glass. So this is like a dense object, and the constituents behave in a collective manner. And this is something that we want to study again at the LHC, and this will be also a topic that we will study at the future collider in the US, which will be the Electron Collider, which will be built in the Brookhaven National Lab, close to New York. So this is this kind of phenomenon that we studied, because in fact the usual equation of particle physics, what we call quantum chromodynamics, are no longer valid for this kind of behavior. So we need to understand this kind of new behavior, compare the models with the data, and this is something that we are doing at the LHC. Another topic that we are studying, which may be even more strange, for you, but we see it every day at the LHC, is because when we have some proton-proton interaction, there is non-zero probability that the protons are intact after the collision. I always give a kind of everyday image. It's as if you have two big trucks that collide, the two protons, they collide. And after the collisions, the trucks are intact. They are scattered, but they are intact. Plus, you produce some small cars. So this is exactly what we see every day at the LHC. There are two protons collide, and then they produce additional particles in addition to the protons. The protons, they lose part of their energy, so they are, of course, scattered, at some angle. So it is shown here. You see that this proton is scattered at some angle, is red halo, so that we can measure the scattered proton in dedicated detectors. Plus, we produce many things inside the main detector. And we study this kind of events that are very interesting. And this, one of the consequences, was the discovery of the Alderon that I will mention in a minute. So let's go, first of all, to give an example of everyday life to make you understand what is the elastic interaction. I think all of you have already played pool. You know playing pool. And when you play pool, you send a ball against another ball, and usually the ball is not destroyed, obviously, but they are scattered at a given angle. So they can lose or they can gain some energy. So what we do when we study elastic scattering at the LHC is exactly the same. We send one proton against one proton, and they remain intact after the collision, but they are scattered at small level. You have to imagine that the protons are the same as these balls when you play pool. Basically, they just scatter. And this is what we want to study. And this we can do both for proton-proton or for proton-antiproton interaction. So this will be, there will be two slides that are a bit technical and a bit more complicated. But the right drawing was what we call a Feynman diagram. And the Feynman diagram, it means that time is moving from left to right. So you see my two incoming protons on the left, then they interact, there is this kind of interaction, and then you have the outgoing proton on the right. So it shows a proton-proton interaction. And these two protons on the right, they exchange this kind of a string, which is in the middle, that represents a gluon. So there is a gluon, which is exchanged between my two protons. And a gluon has the property to emit many gluons. It's always the case. A gluon, if you want, doesn't like to be alone. It always emits many gluons. It radiates a lot. So, and when there is gluon radiation, in fact, the protons are destroyed in the final state. So this is not possible to explain the fact that the protons are intact in the final state. But this is the left diagram. What you see, this is again this kind of a string that I represented between my two protons. And these strings represent either 2 gluons, 3 gluons, 4 gluons, 5 gluons, as many as you want, but not 1 gluon. Because if there is only 1 gluon technically it exchanges what we call color, and in that case, the protons are destroyed in the final state because color has to be conserved. So this is basically the reason why the proton has to be destroyed in the final state. But it's a bit technical, so just remember that if we want 2 protons intact, you need to have either 2, 3, 4, 5, 6, 7, well, how many you want beyond the direction, but not more. This is basically the message of this slide. And this will be some consequences for the Oderon discovery. Because again, it's a bit technical, but the way that there can be 2 gluons, 3 gluons, 4 gluons, and so on and so forth that are exchanged. And in fact, the probability of interaction with 2 gluons, or a odd number of gluons, or an even number of gluons, is different. This is what we call in quantum mechanics, for people who have studied it, the difference in C parity, charge parity. So that's why, in fact, the big consequence is that when you compute what is the probability to get the proton-proton elastic interaction, this is the sum, this is the 2 small equations that are here on the right, the sum of the odd plus the even part of the amplitude. Whereas when you consider P an antiproton interaction, this is the difference of the even and the contrary to what has been done here. In fact, in the translation there was a mistake. It should be par minus impar. But it's not a big mistake. There is a mistake when people translate it into Spanish. So you have for APP is the sum of par plus impar, the sum of the odd and the even part of the amplitude, and for PP bar this should be the difference. So it means, and this was the idea we had to look for the Oderon, if we observe some differences between proton and proton-antiproton interactions, maybe this could be some evidence of this new Oderon particle. And again, so pomerons, what you call pomerons is an even number of exchange that is happening between my 2 protons, so 2, 4, 6, 8, 10, and so on and so forth. Whereas we are talking the Oderon, it's an odd number, that's why we call it Oderon. It's basically so 3, 5, 7, 9, and so on and so forth. So this is, so if we observe the difference between proton-proton and proton-antiproton interaction, this could be explained by the existence of the Oderon. And this is what we saw last year for the first time. Oops. So I just mentioned that the PP bar interaction are coming for the tevatron. So maybe you heard the tevatron was an accelerator that was close to Chicago. It's closed now, but it was colliding proton and antiproton. And the data were coming from the D0 experiment. So I was and I am still member of the D0. And now let me show you the results. So these are the difference in blue. You have the proton-antiproton measurement at the tevatron, so for PP bar interaction. And in red, the measurement from totem, so basically from proton-proton interaction at the Large Hadron Collider. And you see clearly that the data are not compatible. I mean, you see it by eye, that definitely both data sets, the blue point and the red point, are not compatible between each other. So the way to interpret this difference was definitely because of the existence of the Oderon. So this was the way that we discovered last year the Oderon by showing some difference between proton-proton and proton-antiproton interaction. And this led, I mean, to preserve also the work in Mexico, the fact that I got the honor to receive the gold medal of the Mexican Physics Society, the Particle and Field Division, just a few days ago, basically. It was given a few days ago. So now let me come to another topic, which is more pure standard model physics. So you heard probably that maybe we don't live in just in 4 dimensions. It will be 3 space dimensions plus 1 time, but maybe gravity is in much higher dimension. It can be a 25 dimension, 27 maybe, so much higher dimension. So we are trying to look also at this about the LHC and look about the existence or not of extra dimension in the universe. And I will present one of the ways which consider also intact protons in the final state, because it's something I proposed 10 years ago now, and this is becoming a complete reality at the Large Hadron Collider. All the experiments at the Large Hadron Collider are following the method I proposed some time ago. So what is the idea? So this is again this diagram which you have on the left. This is the same as before, Feynman diagram. On the left you have the incoming particles, microphotons, And on the right, my two outgoing particles. You see that the two protons are intact, and then we produce some two gammas, so we produce two photons. So if you think about it, this is something which is not trivial. I mean, you see that there is one photon emitted by each of the protons. They interact and they produce two photons. That's exactly what I wrote on the diagram. So what does it mean? Is that we have some light by light interaction. So light is interacting with light. It's exactly what we show in this diagram. On everyday life, you don't see that. I mean, this light which is emitted here will not interact with the light which is on the left. So this is really a pure quantum effect that we see at the particle level. We see these light by light interactions, and we see it every day at the LHC. And why is it very interesting to study this kind of events? Because we measure all the particles that are produced after interaction. So you measure the photons, and you measure the photons that are produced. You see all the particles. There is no neutrino which escapes, for instance. We measure and the photons are not destroyed. So it means that the kinematic information of the two protons and the two photons should be the same by definition. Because in fact, because of conservation of energy and momentum. So this should be the same information on the photons. So what we need to find at the LHC is some events that are called pilot. So what is it? Because you have these events on the plot, is what is interesting us, where you have two intact photons plus two photons that are produced. That's what we mentioned. But the LHC, you should not imagine that it's just one proton colliding with one proton. It's packets of protons that collide with packets of protons, and millions of protons that collide with millions of protons. It means within the same bunch crossing, you can have many interactions, and up to 50 interactions. So it was representing at the bottom, you see one interaction in one of these stars that produce the two photons, and for instance another one that produces the two photons. And the fact that we measure all the particles in the final state, let me go back to the diagram, shows that by energy conservation, the kinematic properties of the two photon system and the two proton system should be the same for the events we are looking at. Whereas for pilot, my protons have nothing to do with my protons. That's why there is no kinematic conservation. So it's maybe a bit abstract, so let me go to the plot. So illustrated on the two plots in the bottom, we show the ratio of the mass of the two protons divided by the mass of the two photons, and on the right, the difference in angular distribution between the two protons and the two photons. The signal is in black, you see it's picked around 0 or around 1, and this pilot background that I just mentioned is red. So you see that it's a very good way to get rid of the background. If you cut around the peak, you will get a very small amount of background. So that's why it's a very clean way to select these events that could be signal, potential signal of a dark matter or also extra dimension in the universe. So this is a nice way to select this kind of events. So I just want to say that this is a way that we are also looking at the axion particle that could be a dark matter candidate. The same way, so it's a bit technical slide, but photon, which produce a new particle that I call X, which then integrates into two photons. And there is a diagram here which is coupling versus mass of the axion. And you see the grayish area is the area that we can cover using the method that I just did. So this is a method that we are using today in CMS and Atlas, and this is bringing the first result nowadays. But so far we didn't find any new particles, so we put limits, but at least we are looking at who knows, maybe we'll see something new. I want to finish to discuss another method, and very briefly some application that we can be used for this, is measuring the time of flight of the photon. Because the idea, we are looking at these two diagrams that are here. If you measure very precisely the time of flight of the photon, and we will see in a minute how precisely, in that case you can be sure that the proton originate from the same interaction point as the that produced, for instance, by two photons, or can be other particles that are produced. Simply by counting measuring what is the time of flight of the photon to reach the detector. Because we know, of course, precisely the distance between the detector and the interaction point. And in addition, with the precision that we did about the time of flight of the proton. So when you measure time in everyday life, I mean, you are like this rabbit, he is clearly in a hurry, like we were today because we were late. So basically you measure time, And what we measure time is seconds, minutes, I mean, this kind of stuff. So if it is my clock or the watch that I have here enough to measure the time of the proton that we have at the LHC. So this is also something that we have experienced all the time. This is a thunderstorm. So what you see or what you hear at the thunderstorm, first of all you see the thunder, and then maybe a few seconds or a couple of minutes later you hear the noise of the thunderstorm. It's the experience that everybody has seen. And why is it like this? Because the sound is going at about 343 meters per second, whereas you know that the light is going at 300,000 kilometers per second. So the light is going much faster than the sound. That's why the light is coming to you almost instantaneously, whereas the sound is taking some time because the velocity is not that large. So it's what you have seen at the end. And our photons are going at the speed of light. So if we want to get some precision, a time precision of, let's say, millimeters, then we need to get some detectors that are working at 10 picoseconds. So we need to measure the time at the picosecond level, let's say 10, 15 picoseconds. So we need this kind of precision on the time measurement, which is not something easy, it's not technical. So we work on this, in Kansas, and the way we do it, we use, first of all, ultra-fast silicon detectors, because the duration of the signal is a few nanoseconds. So it's very short signals that are produced. And then we use the very fast sampling method to measure the signal. So these are these yellow crosses that are along the signal. So we do this with very fast sampling. So doing this, you measure the shape and also the height of the signal, because if you do a very fast sampling, you can reconstruct the full signal. And again, the duration of the signal is about 2 nanoseconds. And this will give you a timestamp, if you consider like here the decreasing part of the signal. This will give you a timestamp when the signal arrived in the silicon detector, or basically when the particle crossed the detector. And this gives you typical precision per layer, which is of the order of 20 to 25 picoseconds, using this ultra-fast silicon detector. I just want to mention two applications. The first application is a project that we have with NASA. So we will launch it next year because there was some delay, and it's launched by the US Army. So we need to wait when they have a rocket which is available. So we know, of course, since it's secret, we have no information on this, unfortunately, but okay. So basically what we do is exactly the same. We have different layers of silicon detector, and we measure the signal when there is a particle that stops in a given layer, what we call the bragg peak. And when you reconstruct fully the bragg peak, you measure the duration of the signal and also the amplitude of the signal. You can have particle ID to know in the cosmic ray if it was a proton, if it was helium, if it was lead, and at the same time also measure the energy. So this is what we publish, using the method to do this measurement. And the other method, that we want to use, the same idea before concluding, is the same, using the same kind of detector for people who are treated, for instance, for cancer, especially using very intense beams, because we can count the number of protons that are crossing the human body. And there are new kind of treatments that are being used right now in the US, which are called flash beam, like for tumors in the brain and so on. And as far as I know, we are the only people that will be able to measure those. So this is also a very important application of this kind of detector. So this brings me to the conclusion. So I discussed many topics related to the LHC. So first I showed you a bit what is the LHC. I discussed how we do some analysis, and I mentioned the discovery of the Oderon. I didn't discuss the Higgs because I think probably you had already some talks before about the Higgs discovery. And then I discussed also the way that we can approach either the extra dimension or the axion-like particle in the universe using this kind of techniques of measuring photon. And finally, I discussed very briefly this ultra-fast silicon detector. And if you have still 10 minutes, I could show you a small movie which shows you basically how it looks like in reality, how a detector looks like. So this would be the Atlas detector inside the camera. So I don't know if somebody can launch the small movie. So it'll be about a bit less than 10 minutes, so not too long. In the meantime, I will sit down. the detector.
Geneva, Switzerland, home to the United Nations, World Health Organization, Red Cross, and CERN, the European Organization for Particle Physics. 100 meters below the French Swiss countryside, stretching from the Geneva airport to the Jura Mountains, lies a 27-kilometer-long tunnel, housing the Large Hadron Collider. Inside the tunnel, protons are accelerated to nearly the speed of light by strong electric fields, guided by superconducting magnets and made to collide at 4 different locations. The Atlas detector sits at one of these locations, where it observes and analyzes living particles produced in the collisions. It is composed of several specialized layers, each used to identify particles and to measure their properties. Here, at the heart of the collision, is where the mystery lies. The discoveries made in Atlas will answer some of our most fundamental questions. Why do particles have mass? What are the fundamental building blocks of nature, and how do they interact? And is there one theory that describes everything? The construction of the Atlas detector is an impressive achievement by an international collaboration over the span of 18 years. Scientists and engineers came together to contribute to the design and construction of the experiment, as well as to the development of the software and the computing required to run the detector and analyze its data. The various components of the detector were constructed all over the world, then shipped to CERN, assembled, tested, and lowered into the Atlas cavern one by one. In a little over 5 years, the entire detector was assembled in this manner, much like a ship in a bottle. Here we see the assembly of one of the 8 Atlas superconducting toroid magnets. Each 100-ton magnet coil was lowered individually through the shaft and then assembled to define the characteristic size and shape of Atlas. The central components of the detector were assembled individually and then slid inside the magnet structure. They include calorimeters to measure energy, and at the very center, a tracking system designed like a precision camera to take high-definition images of the tracks of charged particles. If the detector were a camera, it would be a 100-megapixel device capable of taking 40 million photos per second. This giant wheel, located on the far end of Atlas, is more than 6 stories tall and is the largest single piece in the cavern. It completely closes the end of the detector, so that absolutely no remnants of the collisions can be left undetected. Despite its enormous size, the positions of its internal components are known as accurately as the thickness of a few human hairs. The completed Atlas detector is 27 meters in diameter, 46 meters in length, and weighs 7,000 tons. That's equivalent to the weight of the Eiffel Tower in Paris. tubing pipe inside which the collisions occur, and is designed to maintain the integrity of the beam and to protect the sensitive components of the detector near the beam line. This is the last stage of preparation before closing up the cavern and turning on the accelerator. Once the cavern is closed, an electronic system prevents anyone from entering the cavern while there is being any LHC. Above the detector floor, physicists in the Atlas control room prepare the detector for the injection of beam. The LHC collides up to 40 million bunches of protons together every second at the very center of the detector. As particles produced in these collisions fly through the detector, they leave traces that are read out by electronics at nearly 1 million gigabytes per second. A complex system of electronics and fast software is then used to filter the data, selecting only those collisions that contain interesting, potentially new and exciting physics. Today, 3,000 scientists from 175 institutions in 38 countries around the world are actively analyzing the collisions produced by the LHC and measured in the Atlas detector. Like a powerful telescope that peers far into the heavens, Atlas is able to explore the internal universe and to examine our most fundamental components. Only by exploring this new frontier can we find answers to the most fundamental questions of mankind. What is the universe made of? What are the rules that govern its evolution? What are its origins? And what is its destiny?
So I don't know if some of you have visited CERN already, but it's definitely impressive to visit the detector, especially when there is no beam. You can really see the detector, which is like a cathedral. So it's really impressive to see. Okay, so I guess if you have some questions now, so thank you very much, first of all. Some questions or comments? Yes. So I don't know, do you want to shout or do you want to microphone?
Hello. First, it's a pleasure to meet you.
Thank you. Nice to meet you. Thank you.
I have a question about the momentum and the program.
Yes.
So that way.
Show back maybe the slides. Yeah, sorry. Yeah, so full screen. So go at the beginning, yeah. I made a mistake. I forgot to show that one. I just show you again the funny captain. That one, yeah? Yes, yeah.
I don't understand the mechanic of that part. How that the momentum increase the quantity of.
Remember, because in fact, when it's a kind of statistical, you can say it's properties if you want. If you have, let's say, 3 objects right, on the left, in average, they will get 1/3 of the momentum. But if you have 100 of them, in average, they will get 1/100 of the momentum. So it means that when you have many partons, they will have less and less. The probability would be to have less and less momentum of the proton per parton, statistically. So this is what, of course, I mean, there is a distribution. We don't have the same value for all the partons for the constituent, but just statistically, the probability is to get 1 divided by the number of partons times the number of the proton. That's why it's going to be smaller.
And the momentum in that scale works the same way that in macro scale?
So the momentum which is taken away by the constituent of the proton. The microscope is the photometric power. So this is the way you see the details inside the proton. Because if you have a bigger microscope, then you will be able to see more details inside your protons. So that's why these are the two variables, momentum and resonant power, how we describe the structure of the proton.
May I ask another question?
Yeah, maybe let somebody else, and then I come back to you. If somebody else first, and another question, yeah? Just here.
Okay, there's easy addition geometry can solve the charge Warren symmetry problem with the quantum chromatology.
Sorry, I could not hear.
It's a
Maybe I can read. Yeah.
Read?
So I read it. So is it the oops, different way?
oh.
So which one is it? So the one is the axiom the only particle that can solve the CP symmetry problem in quantum chromatology. So it's a very dedicated question, and the answer is no. I mean, the axiom is one of those models that could, and it's always model dependent. So you could think of other models that could solve this problem. I mean, some of them have been solved already, and you could always think that there may be some model we even didn't think of that would be the new possibility, basically. So what we want to do experimentally is to have, as much as we can, some model-independent way to look for these particles. Like I told you, for instance, it's an axiom, gamma-gamma going to axiom decays into photons, but you could imagine it could be something else. And we would be happy if any beyond standard model particle is produced, or also in loop of standard model, beyond standard model particle, that modifies the cross-section to produce 2 photons. So we want to have some experimental way to be sensitive to many different kind of models. And then we exclude them because we never saw something beyond the standard model, but we hope one day that we will see some excess. And then, in the second part, will be to understand what is this excess made of. By, for instance, topological properties, angular properties of the events, you try to see which models will be more favored than the other if you see something. But we want to be able to exclude or to be sensitive, let's say, to different models within the same kind of experiment. This is the best, because you don't want, there are so many models that exist that you don't want to have one search for each kind of model. I mean, this would be a huge work and many people. Does it answer a bit your question? Yes. Yeah. Somebody else? Yes? It's a right row here.
Well, I was wondering if you could provide us a way to communicate with you.
Yes, I mean, by the easiest way with my email.
Yeah.
I don't know, maybe this can be given to you. My email is Christophe, which is my first name. Christophe, Chrisistophe, so the French name. Dot Royon, which is ROYON, like Nancy, at CERN.ch. So this is my email at CERN. Is that okay?
We can share it afterwards.
And you can share it afterwards.
No problem.
Christophe Royon at CERN.ch. I can write it and you can share it with your friends. I think it's like an autograph, yeah? Because so I hope you can reach me. Okay, so who else wants to ask you a question? Yeah? Go on this one. Each of you will ask a question.
Okay, I don't really understand why there is a elastic collision between two protons. Why can there be just one I forget the name. Yes, one
Exchange.
Yes.
Yeah. There can. Okay, let me go back to this diagram. For a little bit later. I'm going the wrong direction. Yeah, c'est the diagram. There can be a gluon exchange between my two protons, and they can produce, you see, all these gluons that are there. But in that case, the protons will be destroyed in the final state. They will not be intact. Whereas what we consider in the following part is the case when the protons are intact. Like I said, this accident of the two trucks and the trucks are intact. So we were considering only these very special events. But if you don't request the protons to be intact or if they can be destroyed, then there can be a gluon exchange between the two protons. It's not a problem. But then you produce many gluons between many particles. You see all these gluons that are produced. And in addition, the two protons will be destroyed. So this is the difference. So the advantage of having the intact protons is that to detect all the particles which are produced. Because when the protons are destroyed, you should imagine that they go at an extremely small angle. So a big part of the decay product of the protons, they escape through the beam pipe. And you cannot measure them, of course, because this is where there is the beam. So that's why you cannot detect all the particles that are produced. It's not what we call a 4-pi detector. There are some particles that disappear through the beam pipe. That's why the advantage of getting the intact proton in the final state is that you detect everything. Of course, the price to pay is that you have a lower cross-section, so less events are produced. This is the price to pay for this kind of events. So should we come back to you? So are there other questions on this side? So maybe, yeah, or maybe I'll come back and then I could take you.
Thank you. I was wondering the part of the explanation, I don't get it, the part of the other one.
Yeah, it's difficult.
Important.
It's difficult. So let's go back a bit. Yeah, this is a difficult thing to explain by hand, actually. So the other one, because they, in fact, you can see that there is either an odd or an even number of gluons that are exchanged. Yeah? So when we have an even number, we call it chronoron, and when there is an odd number, you get a hoderon. Even if this is already approximate, what I'm telling you now, but okay, let's get it. And this gives different C parity, what we call so different quantum properties of the exchange. So that's why, I mean, in that case, that's why they lead to the probability of the interaction of keeping the two proton intact, so elastic interaction, is the sum of the even and the odd part of the interaction. Whereas for proton-antiproton interactions, since you have an antiparticle, this is the difference of the two. So that's why you see the difference as a consequence of the quantum properties of the object. This is a bit, I mean, to tell it a bit by hand, what is characteristic of this other one. You can see it really as a odd or even number of gluons inside this exchange. I cannot say much more because then we will have to go through, of course, of the technicality and the mathematics of it. Which should take us probably the full night, again, at least the full night. So who else have a question? Yeah, I will come back.
Well, first of all, thank you very much for the talk and congratulations on your work.
Thank you.
I have a question about the future of particle physics. Exactly, what does it suggest that we need to increase energy to observe some phenomena like supersymmetry or maybe reaching to other events?
Yeah. So this is of course always a tricky question. I mean, where should high energy go? Is it going to higher luminosity or is it going to higher energy? So it's clear that going to higher luminosity is easier in the sense that you keep the same tunnel, you keep the same machine, and this is what we are going to do at the LHC. But if you want to see some beyond standard model particle that will be produced at the high luminosity LHC, it's clear that there needs to be some hints before. I mean, it will not be 5 sigma, but there needs to be some hints here and there that it's not compatible with the standard model. And I mean, so that's why it will be important in the data that we are taking now in the next runs, I mean, like the next 3 years. It will be good to see if we see some excess, which probably will be the case statistically. And then it's good to have some higher luminosity to check if this excess were just purely statistical or if it was indeed something that appeared. But if you want to have a higher probability to produce a beyond standard model particle, the center of mass energy is really the critical point. I mean, and for this, you need to go to the new machine, FCC, for instance, at CERN, that's an example, but it's not for tomorrow. I mean, next time, and unfortunately, the cost is getting higher and higher because it will increase the size. So in parallel, I think there must be some technological developments, for instance, using plasma accelerators that will allow you to get higher energy in a much more compact way. I mean, if you have a plasma accelerator and you are able to have some reproduction, because now there is some possibility to get acceleration, to get plasma, but it's not well reproduced. So you cannot get a perfect accelerator that will produce particle at a given energy for a long time. So, or the other possibility, but again, it's not something easy, is to go towards a muon collider. Muon collider, within the same circle, you can have much more energy for the muon. But again, it's not for tomorrow. But at the same time that we are discussing the FCC, which is technical point of view, I would say it's close to what we are doing today. There is no breakthrough, so we'll be able to do it soon. But with the high cost, because we increase the size of the machine, we need to have some pure technological development that will allow to get higher energy with a more compact machine. I think both should be developed. So who else has somewhere? I see 2 hands. Thank you.
Hi, nice to meet you. I don't understand how do gluons change color.
The gluons, sorry?
How do gluons, the gluons change color?
In fact, a gluon, I mean, it's also comes from a theory that we call quantum chromodynamics, describe the interaction between quarks and gluons, and the gluon carries a color and an anticolor. In fact, a bit. That's why the only way to have a zero color that can be exchanged is to have a minimum a pair of gluons. Because one single gluon will carry a color, for instance, like when we are showing all these different colors, one given color and another anticolor. So that's why they cannot be a colorless object. And this is coming, again, it's the theory of quantum chromodynamics. And the color, when we say color, you should not imagine, of course, that this will be a gluon which will be the color of your t-shirt or something like this. It's just a quantum property. Physicists have some imagination, that's why they call it color, in the same way that they call the quark beauties. I mean, of course, it's nothing, it's just name, which is like this. It's just related to quantum properties of the objects. Who else? The last row.
Hello. Good afternoon again. Thanks a lot for the talk. I want to say that I think that's a very interesting talk. The mechanism of how the proton with proton interact and how the gluons interact with themselves to find how these new particles, Omeron and Oleron, because these particles was until the last year, I think, theoretical particles. So my question is is aligned to the fact, to the particle physics in the future. Do you think there is more experiments that provide us information about new, more theoretical particles like gravity or something like that? Do you think that?
So it's a tricky question because I mean, of course, I don't know what nature chose. I mean, the only thing we can do is to look, I mean, and see if there is something which was not expected. So if like we did for the Oderon, it's the same. You were mentioning people were mentioning SUSY particle or also graviton. So the only thing we can do is to look for them and see if they exist or not. So we hope that there may be something new appearing at the LHC and the new data that are coming now, but who knows? I mean, I cannot, of course, say for sure that we will find something. So I would just say stay tuned, and maybe the cartoon that I didn't show you at the end, I can show it to you briefly now. You see that's a bit funny. Yeah, here it is. So you see there are these people that are in a safari in Africa. They are looking for animals on the right, and they don't see the lion, which is just sitting on the left. So as physicists, we should not do like these people on the safari, but we should look everywhere. And who knows, maybe we'll be lucky. And we already discovered the Higgs boson and the other one, so maybe we'll discover something more in the next year. And so that's why we need to look and see.
Exciting.
Yeah.
I think it's different energy of the collision for proton, 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 proton.
Yes.
So you assume some shift of the energy. Well, the second is the nature of the other one is kind of different from the other particles, like the atoms. No? It's more of the I don't know. It's a particle problem.
It's not
Something like that.
It's even not a particle yet, maybe I can answer both questions. So yeah, so thank you for the question. Of course, I didn't enter in all the details, but it's true that in fact the measurement of the teratron for P-figure interaction was about 2 TeV, 1.96 TeV exactly. And at the LHC, we had data at 13, 8, 7, and 2.76 TeV data. So what we had to do to show the plots that I yeah, here it is. So what we call here the total measurements, we had to extrapolate it from the measurements at the LHC at this energy, as I said, 2.76, 7, 8, and 13 TeV, down to the teratron energy of 2 TeV. So the way we did that is by identifying the properties of elastic PT interaction, which always show the same shape, let's say, for all square root of S. So it's always going down, then there is what we call a dip, then there is what we call a dump, which is the maximum, and then it's going down again. So we measure all the characteristic points of the shape of this elastic cross-section behavior to extrapolate them to the teratron energy to be able to produce the red points that are in this figure. So this is true that it's not direct comparison. And why is it like this? Because running the LHC at the same energy at the teratron is very difficult from the machine point of view. And in addition, we would have zero acceptance in the domain when we compare it in the minimum and the maximum of the data. So even if we are running the LHC at 2 TeV, we would not be able to measure this quantity. So that's why we did this strategy. And then concerning the other one, you say it's not like electrons. Yes. In fact, I mean, I didn't want to stress it because it's really technical. It's something that you exchange. It's not a particle. You will never observe a pomeron or an oderon. It's not like you say you will observe an electron. Pomeron is not the same. The oderon is not the same. It's not a particle that you can observe. So this is true. It's an exchange between two particles, and the exchange of two particles represent the interactions between the two different protons, for instance. When there is a pomeron or neutron which is exchanged, this is the way that there is interaction between the two protons. But it's not a particle that is really produced. So, and again, it's a bit technical, that's why I'm important in all the details. Yeah?
Okay. We need to make an algorithm to build an accelerator in the space.
I would say, first of all, it's not easy to do, obviously. I mean, you have to bring the magnets and everything into space, and you pay per gram, I mean, when you send it into space, so it's not easy. But let's assume that, I don't know, many hundreds of years, we have some base on the moon, why not? And we could have it there on the moon. It's easier, but have it purely in space. So I would say there are one inconvenience is related to cosmic rays, that's for sure. Because the cosmic rays, I mean, we are protected at least on the Earth, and we would need the same kind of protection on this accelerator. Of course, then there is the advantage that we don't need vacuum or this kind of thing. This would be one advantage. But for sure, if it exists one day, it's not for tomorrow. But the cost nowadays would be enormous. I mean, the technology, you have to bring everything. So how many rockets you would need to send and so on, it would be really enormous, for sure. When we see that it's already so difficult to build something in space, I mean, where we can send people to the moon or rather later even to Mars. So this is the same, even more difficult, I would say. So.
Can you comment a little more about the application? Because you say some words about the gravity, and we have many students from the medical physics.
Okay. Yes.
Regarding the possibility of
medical part. So the medical part, actually, we just got it approved by NIH, which is the National Institute of Health in the US. The project is to use the detector that we are using, the ultra-silicon detector that we are using in high-energy physics, but for medical application, using the same kind of technique of fast sampling that I described. And what we want is to start by doing simply a quantic experiment. See if we have very short signal, which are nanosecond signal, you can count the number of protons that are going through the human body when people are treated for cancer, for instance. And especially there is new techniques that are being developed now in the US, what they call flash therapy. So we use very high intensity beams for especially some brain tumors, for instance. And for now, as far as I know, I'm discussing, again, I'm not a medical doctor, so I don't know if I'm a specialist, but as far as I know, the doctor told me, nobody is able to measure the dose for this flash therapy treatment, which is of course very important, because if you are not able to measure, deliver the dose which is delivered to the patient, I mean, it's catastrophic, obviously. So that's why we made a proposal, which was well received by NIH, which should be starting getting money at the beginning of January. And we are sure to be funded because we were classified among the 3% best project in the US for medical physics. So it's not my specialty, obviously, it's more, as you can guess, high energy and nuclear physics. But I was thinking, it's good to use something that we develop for our field in other domains, so medical physics, and also the cosmic ray physics that with the detector that we send into space. So this is something where, that's why we will soon, we need definitely some people, I mean, to come to Kansas to help us on this. People who are experts, for instance, typically on electronics, because what we will have to change, we have electronics, which we did for energy physics or for NASA, but the electronics has to be adapted to this measurement of the radiation for the medical application. So this definitely will be looking for postdoc or students who are interested in for this project in Kansas, for sure. So next week I will be also in Hermosillo to discuss about this. And the idea will be to have some collaboration both with Puebla and Hermosillo in Mexico about this topic and this application. So if some of you are interested, please contact me and we'll see how we can move forward. But definitely, I think this is very important to make this kind of development, since we have the experience for energy physics, and this could be a kind of return for everybody in the world, I'd say, for the people, general people life. For cancer treatment is an important topic. So that's why, again, it's not my specialty, I'm not a medical doctor, obviously, but I think this project that we did is together with the hospital at the university. So we have it in agreement with the hospital.
So you are wrong in the
Yeah, of course. I mean, this is a big, I mean, exactly. This would be a good idea to have more collaboration, because what I think also for me, I mean, for tourism, at least tourism, to collaborate with Mexico. Between the US, it's a bit natural because we are just neighbors, I must say, so it's normal for us to collaborate. And also, I mean, I am not American, I'm not US citizen, but I am French citizen. So we have, of course, the same kind of Latin culture, which is also what I think is different from the culture in the US. From this point of view, it's closer to the Mexican culture, than the French culture. Yeah. So it's more personal.
Excellent. No, hay que agradecer al profesor.
Thank you.